In section 3.4, we are going to talk about the derivative as a rate of change. We will talk about the instantaneous rate of change of the function, given function f. This rate of change is going to be with respect to the variable x at a point x0, and we talked about that this is the same as taking the derivative at the point x0, and the formula is again the well-known limit definition of the derivative, which is limit h goes to 0, f of x0 plus h minus f of x0 over h. Of course, we always assume that the limit exists, otherwise it doesn't make sense. Okay, so let's look at this. This picture shows a moving object. Okay, so the first position is actually the position of the object at time t is represented as s is equal to f of t. So f of t represents or shows the position of the body of the object that's moving along the coordinate x s coordinate, and after time passes, delta t many time passes, the new location is s plus delta s, because the object is going to move delta s more on top of s. And after delta t minutes or seconds or unit time, the object is going to move delta s meters or kilometers depending on the unit. Okay, it shows that. And this is the same. So whenever we use that f, instead, what we get is instantaneous rate of change of the speed, okay, at a given time. So here is what we get afterwards: velocity, which is the instantaneous velocity. It is the derivative of the position function with respect to time. The position function is s. We represent s as f of t, of course. If a body's position at time t is s, which is written in terms of f of t, then the body's velocity at time t is v of t, which is the derivative of s function, and it's the limit as delta t goes to 0, f of t plus delta t minus f of t over delta t. Next, okay, again, this is telling about the motion, and the motion, the position function is s is equal to f of t. The motion is along a straight line s, okay, and this position this time is the vertical axis, as you would see, and time is the horizontal axis, as you would see here. And we know the derivative of s with respect to t is going to give us the velocity, okay, velocity, and as you would know, dSdt is the derivative of this graph at the specific time t. Okay, so let's look at these graphs separately. In the first graph, s is an increasing function, and if you draw tangent lines, okay, if you draw tangent lines, the tangent lines are going to have positive slopes, which is going to tell us that the speed, the velocity is positive, so the object is moving in the positive direction, okay, with a positive speed, okay, and right, so let's look at the second one. In the second one, as the position change, the position was in here, but then it comes back, it drops down to somewhere close to 0. Of course, when you have that, if you draw the tangent line here, tangent line is going to have a negative slope. dSdt is negative, which means velocity is negative, okay. So the object's direction is negative. In the opposite direction it's gonna show, because velocity is negative in here, okay. So this velocity being negative or positive is just related to the direction of the motion here, okay. So what is speed then? I mean, speed and velocity are two different notions. Speed has no direction. Okay, velocity has direction. Velocity can take negative values, but speed has no direction, and speed is always positive or zero. Okay, so we can easily define this as speed is the absolute value of the velocity. As you would see here, speed is equal to the absolute value of v of t, which is equal to absolute value of ds dt, because we just saw that the velocity is ds dt. Alright, so let's try to understand this graph. I will try to make it a little bit bigger. So this is the velocity graph of a particle moving along a horizontal line. Okay, let's try to let's look at this graph and understand what's going on. So we have the horizontal axis is the t, which shows the seconds, which is the time in seconds, and the vertical axis is v, which shows the velocity. Okay, as time increases, as you will see, there's a line here, and the speed is increasing, of course. Okay, so it's moving forward because the velocity, this is the velocity, so it shows the direction. Our object is going towards, let's say, whenever velocity is positive, we are assuming that the object is moving towards right. Okay, as you will see here, in the first second, speed is increasing, and between first and second the speed is constant. So it says it is steady. Okay, and afterwards 2 to 3, the velocity is getting smaller. Okay, in value, speed is getting smaller, so that is showing us that the object is slowing down. Okay, here it is speeding up, here the velocity is constant, the speed is constant, and here this object is slowing down. Okay, in this first blue part, the velocity is positive. Be careful. Whenever velocity is positive, it is moving forward. But if you look at 3 to 5, you would see that the velocity is negative, right? It's under t-axis. So it is since the velocity is negative, it is gonna tell us that the object changed the direction. It's moving backward. Okay, moves backward. As you will see here, v is less than 0. When it's moving backwards, you will see that when the absolute value of velocity is getting bigger, it is speeding up. When the absolute value is getting smaller, it is speeding down, which is slowing down. Okay, and the greatest speed, the fastest speed, is at this point. Be careful about that. And now from 5 to 6, as you will see, the velocity is 0. And then from 6 to 7, it is speeding up again because the velocity is bigger than 0. It is moving forward again in the positive direction. Okay, remember that the velocity is the derivative of the position function, and this graph is really meaningful. So I would encourage you to understand this graph. Okay, this is time versus the velocity graph. Let's look at the next one. From here, we next step, we talk about the acceleration. So far we talked about the position function, which is s, which is equal to f of t, and then if you take the derivative of s, we get the velocity function, and then if you take the derivative of the velocity function, you get the acceleration. So these are all related to each other. Here, acceleration is the derivative of the velocity with respect to time. If a body is positioned at time t is s is equal to f of t, then the body's acceleration at time t is a of t is equal to dv dt, which is the derivative of the velocity function with respect to time, which is the same as second derivative of the position function with respect to time. We have another notion, which is jerk. Jerk actually the derivative of the acceleration with respect to time. And what is jerk? What is acceleration? The meaning one can discuss, but the main idea here is we are going to look at only in terms of mathematical meaning. and we are not going to get into the details as much. In physics classes you can learn more about the jerk and also the acceleration. As you will see, jerk at time t, it's the derivative of the acceleration with respect to t, and it's the third derivative of the position function with respect to time. Okay, so let's look at this example. Let me see. Okay, so this is about, let's see, this is, let's say at time t is equal to 0, let's say we are dropping a ball from 45 meters high. Okay, so a ball bearing, actually it is falling down from rest, and it shows the motion of that ball. As you will see, in the first second the distance it travels is just 5 meters, but in the second second it is going to travel 15 meters. In the third second, see, it's the third 1 second here, it is going to drop down 25 meters. So it's getting faster and faster, otherwise it wouldn't take that much long, that much long distance, right? So at first the speed is slow, so in 1 second it's traveling just 5 meters, but in the second it is faster, so it drops down, it falls down. The speed is going to increase, of course, increase with respect to, of course, an equation that's going to represent how it is going to change. Probably we are going to see it somewhere. Yeah, for example, here we can see this is a this is a rock example 4, this A. So you are, I think, dropping you have the at time t is equal to 0, there's a rock and you're throwing up, and then when you throw this up, it's going to go to the maximum distance from the ground, and then the velocity is going to be 0, because if the velocity is 0, then it's going to stop at its maximum, and then it's going to start dropping down. When it's dropping down, its velocity is going to increase, and the question is at what time it's going to be 250 feet high if you throw the rock. If you throw the rock from the ground and wait for its coming down. Okay, that's the example 4. One can take a look at that. Let's see B. This shows the graphs of S, which is the distance function, and the velocity function as functions of time. The distance is going to be the largest when the velocity is ds dt is equal to 0, right? Like similar to here, like in the first part A, the velocity is 0, which is ds dt is equal to 0, S is the maximum. And here in the second example, it is the same story. S is going to be the largest when the velocity is 0, because it cannot move any further, the velocity is 0. Okay, it says the graph of S is not the path of the rock. Okay, it's not the path. It's a plot of height versus time. The slope of the plot is the rock's velocity, graphed here as a straight line. So this straight line is going to be the velocity. So at first the velocity is 160 meter per second, maybe, right? Feet per second probably. Okay, the unit. And then it's let's see, at time t is equal to 0. I'm sorry. Yeah, this is another example, by the way. You're not at 5. What is it? At 5, the velocity is 0. S is what? S is 0 as well. So it is going down. Okay. So what this is saying is at 5 it's going to have the maximum distance. Maximum distance is 400. So it is showing this is when the at 5 seconds the velocity is 0, and it's gonna get to the highest location there. Okay, right. Okay, let's read this again. The blue color is the distance function, and the yellow one is the velocity function. At time t is equal to 0, the location is 0, so the rock is here, and then after 5 seconds or 5 minutes, whatever, the height is 400, so this is the highest place, 400. And at the beginning the speed was 160, but whenever S max we have, the velocity is 0, and it's gonna go down, and it's going to go down at 10 seconds. It's gonna take 5 seconds or minutes, whatever, to go up, and 5 minutes to go down in the ideal situation. That's what it shows here. Okay, next example is about the cost function. The x-axis is showing the per each week how many tons of steel production. Okay, how many tons of steel is produced per each week. The x-axis shows and the y-axis shows the cost. How much does it does it cost to produce that much amount of steel? Okay, so Cx is the cost of producing X tons per week. The cost of producing an additional H tons is Cx plus H minus C of X. You remember that, right? So this is, then we can find the slope of this red line, which is the slope. We call it marginal cost at X. So it is delta F over delta X, you can say, and delta X approaches to 0. In other words, it's the same as C X plus H minus C of X over H, as H, limit of as H goes to 0. You can find the marginal cost like that. Okay, so next, what is this? This is showing the marginal cost, which is the derivative of the cost function. Okay, so it says, roughly you can say this could be estimated if you just think about producing one more unit. Okay, so you're going to get extra a cost, which is delta C. It is right here. This is just an approximation. It's not really what it is. You can consider that this, if you remember, we talked about the secant lines between this point and this point. What is the slope of the secant line is delta C over 1. Of course, this is not exactly the same as the slope of the tangent line, but you can approximate it, because the real tangent line, the derivative is dc dx, which is this one. So there's just a little bit difference between the two, but it's okay. If there is no way that you can compute, you can just approximate it. Okay. This is another example. This example 7. It's about smooth skin peas. Okay. Okay. Let's see. This is P versus Y. Okay, this is the proportion of smooth skin peas, and then this, you're going to see the dy dp, which is the derivative of this. If you take the derivative of this, you get 2 minus 2p. 2 minus 2p is a line which is a negative slope, and you would see that the slope is negative here. Okay, going down. Okay, the tangent is going down. Why is that? If you draw a tangent line here, they are all positive, but it's getting smaller, right? This tangent line here has a bigger slope than the tangent line down here, so the slope is getting smaller, but still positive though. Okay, this is another example. We don't want to get into details as much. We can solve some problems on that later on.